So this last piece of chapter 1, trying to extend our knowledge of combinations and permutations and polynomials all together, talking about something called the binomial theorem. And the binomial theorem allows us to expand polynomials. And it states that for all positive integers n, and for any real numbers a and x, I can expand any binomial of any to any power by using this summation. So r from 0 to n, as you kind of see throughout the summation here, we have NCR, it's just a combination. We have a to the n minus r, so that just means the first term, and n minus r, you'll see what happens, but essentially that means its exponent will count down from whatever the degree of the expansion is, and x to the r. And that exponent will count up. So you'll see what I mean by that in a second, but I just want to write that in one more time. So n minus r, the power will count down from n to 0, right? As r increases, that number will decrease. And x to the r, the power will count up from 0 to n. And now I'm in the way of my summation. So let me maybe just move this over here. So this summation, if we were to expand the summation, we would get, I'm just going to put it down below, it's easier. We'll start from 0, right? N choose 0 times a to the n minus 0, times x to the 0, which is 1, plus n choose 1, a to the n minus 1, so now that term is decreasing, x to the first, so that term is increasing, right? That's what I mean by this counts down, this counts up, and so on, right? So I'd have n choose 2, a to the n minus 2, x squared, and so on, until I get to n choose n, a to the 0, x to the n. So now you can kind of see, right? You can see this counting down. I just colored the wrong one over here. This counting down, this counting up. Kind of see what I'm talking about now. So for one example, 2 plus x cubed can be expressed as, so the cube tells me I'm going to have 4 terms, right, from 0 to 3. So, well, here's my, let's get our colors again, right? Here would be my a in the general form. Here would be my x in the general form. So I'm going to have an n would be my 3. So I can show that too. So we'll have 3 choose 0 times 2 to the 3, x to the 0, and then I'll have 3 choose 1, 2 squared, right, it counts down, x to the first counts up, plus, oh, let me move this down because I already know I'm going to run out of space, 3 choose 2, count down, count up, and then 3 choose 3, count down, count up. And I know I'm done when my combination, the n and the r, match. So if I were to simplify this, well, I know that 3 choose 0 is 1, 2 cubed is 8, x to the 0 is 1, 3 choose 1 is 3, 2 squared is 4 times x, 3 choose 2 is 3, 2 x squared, 3 choose 3 is 1, 1 x cubed, so I get 8 plus 12x plus 6x squared plus x cubed. And if you don't believe me, you could actually FOIL this out to check it yourself. I'll explain how I know the values of all the combinations, right? How I was just able to pull those out of my head, right? I didn't have my notes in front of me. There's a trick that allows me to come up with those, and I'll show you that in class. That's the investigation that you see at the top of your notes. We can try this one more time. Write the expansion of 1 plus x to the fourth. So I like to show this out in general. So I like to do this first. I personally find, oops, it's going to go up to 4. I personally find that it helps keep me organized just with what goes where. It's 1 to the n minus r times x to the r. So we got 4 choose 0. 1 to the fourth, right, counts down from n to 0. X counts up from 0 to n. 4 choose 1. 1 to the third, x to the first. 4 choose 2, 1 squared, x squared. 4 choose 3. Again, we're counting down with the first term and up with the second. Down with the first term, up with the second. So I know that's going to be, all that just turns into 1, right? 4 choose 0 is 1, times 1 times 1. 4 choose 1 is 4, say 4x. 4 choose 2 is 6, x squared. 4 choose 3 is 4. 4 choose 4 is 1, x to the fourth. Right, so as gross as this formula looks, right, as gross as this expansion looks, as long as you can start to identify that pattern, right, again with our counting down, oops, with our counting down, and with our counting up, as long as you can identify those, it's just following the pattern, and hopefully you don't find that too bad. This last one requires just a little bit of thought. So I want to find the coefficient of this term here in the given expansion, x plus 3y to the sixth. So we can do this without expanding the entire polynomial, and that would be great because something like x to the sixth, we would be here for quite a while. So let's start looking at just what the summation actually means. So my expansion of x plus 3y to the sixth is going to take this form. Well, we'll still have 6 choose r. First term counts down, and my second term counts up. Okay, so if I'm doing this, then I want both of these exponents, we can see from my given, we want both of those to be 3. Those need to be equal to 3. Sorry, that n should be a 6. It should be a 6. So how can I get 6 minus r equal to 3 and then r equal to 3? Well, I kind of just said it right in the logic there. R has to equal 3. And then I can just focus on that one term. So I just want to look at what 6c3 x cubed 3y cubed would turn out to be. And 6 choose 3, I'm just going to do out quick, just because I can't do the trick that quickly in my head without knowing where it starts. So 6 choose 3 is 20, x cubed, and I get 27 y cubed, and 20 times 27 is 540. So my coefficient on x cubed y cubed is 540. Right? When you see a problem like this, and they tell you just find what this one term is, then don't go through the hassle of expanding the entire thing. Right? The point of IB is to work smarter, not harder. So I don't want to go through all the motions of the expansion if that's not what they're looking for. Do just the work that you have to do. We have a way to zone in on this term, and that's just with a little bit of thought, right? Just by looking at kind of where I need to end up and the information that I have.